Friends, today I am dealing with the system matrix for a thick lens and thin lens, the final section of the chapter matrix method in the paper Physical Optics and Modern Optics. Here we are discussing two types of lenses. One is a thick lens and other is a thin lens. First of all, we are going to discuss about the thick lens, and it may be very much simpler if we are discussing the thin lens after the thick lens. Now, we all are familiar with the system of optical system corresponding or dealing with the lenses. That means when a light ray is passing through a lens, it will correspond or it will propagate through the lens by two phenomena. One is a refraction and other is a translation. Here we are dealing with a lens having thickness T. Here T is the thickness of this lens and T is not equal to 0. T is some values greater than 0. T is greater than 0. And a light ray is originating from a point O. That point O is situated in the optical axis of this thick lens, and it is translating through some medium having some values of refractive index, some arbitrary values, and it incident on this first refracting surface of the lens at point A. At point A, this is the point A, and after incidenting at the first refracting surface at point A, this light ray will enter to the lens, and there will undergoes a translational process from A to B, and the ray will or emerges out from this thick lens having thickness T from point B, and this after the refraction from this point B, the light ray goes to the point I, where the point I is again on this optical axis of this lens, and here at the point I the image will formed out. Here we are dealing with what happening or how can we represent the processes corresponding or taking place inside this thick lens. So at the point A, the light ray will enter to the thick lens, and at point B the light ray will emerges out from this thick lens. So we have to deal with the processes taking place between A and B. So at the point A, when the light ray will enters into the lens by refracting at first refracting surface, and I am taking the radius of curvature of this first refracting surface as R1. So the first process is refraction at face or at surface 1, first surface. The first process is refraction at first surface 1. Then the light ray will undergoes a translation from A to B. This translation is taking place inside this thick lens, and I am denoting the refractive index of this thick lens as mu. So the second process is translation from A to B, and at the point B, the light ray will undergoes again a refraction at the second refracting surface, and I am denoting the radius of curvature of the second refracting surface as R2. So the third process is again a refraction or second refraction at surface 2, second surface. This is surface 1 and this is surface 2. This is surface 1, surface 2. So I have to represent all of these phenomena taking place inside this lens by using some matrices. So here I have to deal with the matrix method, and before that I am denoting the I am marking this vertical distance from this optical axis to this point is x1 and this point is x2. So I can represent this point A have the coordinate lambda 1 and x1. Similarly, this is the distance of this lambda 1 or point A from this optical axis, the distance of the point A from the optical axis, and lambda 1 is the optical direction cosine corresponding to the point A. So this point is lambda 1 x1. Here you have to Note that I am not denoting the alpha 1 or angle theta 1 here, because it is already understood by you. So I am denoting this coordinate as lambda 1 and x1 only. This lambda 1 is optical direction cosine. Similarly, the point B have the height from the optical axis as x2. So this point B have coordinate lambda 2 and x2. I am denoting the point A have the coordinate lambda 1 and x1, and lambda B have the coordinate lambda 2 and x2. So I have to represent these two coordinates in the basis of the process taking place between these two refracting surface. So by using the matrix method representation, I can represent this lambda 2 and x2 by a column metric will be equal to, here on moving from A to B, we are taking place three phenomena. One is first refraction, translation and refraction, second refraction. So by denoting these phenomena in the matrix representation, we have to trace, or we have to follow the path of the light ray in the reverse order. So we have to consider the second refraction at the first place. So the matrix corresponding to the second refraction will be 1 minus P2 and 0 and 1, because from moving A to B, we have to on representing this process in the matrix method, we have to follow the light ray in the reverse order. So from B to A, so I am if we are looking for, from B to A, the first process is the second refraction, the refraction at the second refracting surface. So the matrix corresponding to the second refraction is 1 minus P2 and 0 and 1. So minus P2 is nothing but minus P2 is the power of the second refracting surface S2, second refracting surface. The S2 and the surface in the power on P2. And the second process when we are looking in the backward direction is the translation from B to A. So the matrix corresponding to the translation will be 1 0 and T by mu and 1, where T is the translational distance between B and A, and mu is the refractive index of this lens medium. And the final process final process is the refraction at first refracting surface. So the matrix corresponding to the first refracting surface is 1 minus P1 0 and 1 multiplied with the first coordinate lambda 1 and x1, you will get the final coordinate lambda 2 and x2. And again, P1 is the power of first refracting surface, power of first refracting surface. So P1 have values, mu2 minus mu1 divided by r1 is the value of P1. So here mu2 is the refractive index of second medium. So if we are looking in the direction of light ray, the second medium from O to A, the light ray is going from O to A, then A to B. So the second medium is the lens medium. So mu2 will be having refractive index value mu. And let us consider the outer medium is air medium. Here is air and here is air. So the value of refractive index mu is equal to 1. So the P1 will be mu minus 1 divided by the radius of curvature of first refracting surface r1. And again P2 will be equal to mu2 minus mu1 divided by r2. Here mu2 is 1. So light rays originating from light rays going from lens medium to air medium. So second medium is air. This is the second medium. 1 minus mu divided by r2, or we can write it as minus of mu minus 1 divided by r2. Here is r2. Okay, now the system matrix is given by S is equal to, system matrix S is equal to matrix 1 minus P2 0 and 1 into 1 0 T by mu and 1 into 1 minus P1 0 and 1. This is the system matrix corresponding to a thick lens. So if we are multiplying these matrices, we will get 1 minus p2 0 and 1. If I am multiplying these two matrices, 1 into 1 is equal to 1, 0 into 0 is equal to 0, 1 plus 0 is 1 itself, and again 1 into minus p1 is minus p1 plus 0, so minus p1. Again 1 into t by mu is equal to t by mu plus 1 into 0 is equal to 0, so t by mu, and here minus p1 t by mu into minus p1 t by mu into 1 into 1 is equal to 1. So 1 minus t p1 divided by mu, 1 minus t p1 divided by mu, and again these two matrices are multiplying. 1 into 1 is equal to 1, so 1 plus minus p2 into t by mu is minus p2 t by mu minus p2 t by mu, and here 1 into minus p1 is minus p1, and here if you are multiplying this term to this term, you will get minus p1 minus p2, this minus and minus get plus, and t p1 p2 divided by mu, and here 0 into 1 is equal to 0 plus 1 into t by mu is equal to t by mu, and again 0 into 1 into minus this term will get as like this, t p1 divided by mu. So this is the system matrix corresponding to a thick lens. We have in general the values of system matrix, or the system matrix corresponding to a general system have the form b minus a minus d and c. This is the system matrix for a, or general system matrix for any optical system. So if I am comparing these two matrices, I can write it as A is equal to, I can write it as A is equal to, the value of A will be equal to, here negative A is this whole term, I am taking the negative outside, I will get P1 plus P2 minus T P1 P2 divided by mu. Similarly, B will be equal to 1 minus P2T divided by mu, and C will be equal to 1 minus T P1 divided by mu, and again D will be equal to minus T divided by mu. It is the values of the Gauss coefficients A, B, C and D in the system matrix we have obtained for the thick lens T. Here you can see that you have already derived a system matrix for an arbitrary system. That means the distance of the distance between two refracting surfaces taken as D. So these phenomena or these values can be, or this system matrix can be easily obtained by replacing the values in the system matrix of an arbitrary system D by T. D കൊണ്ട് റീപ്ലേസ് ചെയ്ത് കഴിഞ്ഞാൽ ആർബിട്രറി ഒപ്റ്റിക്കൽ സിസ്റ്റത്തിൻ്റെ സിസ്റ്റം മെട്രിക്സിലെ ഡിയെ ടി കൊണ്ട് റീപ്ലേസ് ചെയ്താൽ കിട്ടുന്നത് തന്നെയാണ് ദീസ് വാല്യൂസ്. എനിവേ അതൊന്നുകൂടി എക്സ്പ്ലെയിൻ ചെയ്യാൻ വേണ്ടിയിട്ടാണ് ഞാൻ ഇവിടെ ഒന്നുകൂടി ഡിറൈവ് ചെയ്തത്. എനിവേ ഹിയർ I am taking the condition for image plane. The condition for image plane will be B into D2 plus A D1 D2 minus C D1 minus D. Substituting the values, we will get B 1 minus P2T divided by mu into D2 plus P1 plus P2 minus P1 P2 T divided by mu into D1 D2 minus 1 minus T P1 divided by mu into D1, here this D2 is common multiply, minus of minus will be plus T by mu is equal to 0. So you will get an expression like that. and substituting the condition for image plane in these values of Gauss constant. Dividing throughout by d1 d2, you will get p1 plus p2 minus p1 p2t divided by mu plus 1 minus p2t divided by mu into 1 by d1 minus 1 by d2 into 1 minus t p1 divided by mu plus t divided by mu d1 d2 will be equal to 0. Here we have that the quantity t is the distance between these two refracting surface or the thickness of this lens. T is the thickness of this lens, and d1 and d2 are the distance of the object as well as the image from these lenses. So if we are considering the values of t and d1 d2, values of t and d1 d2, or we are comparing t and d1 d2, you can write it as, or we can see that t will be very much less than d1 and d2. So these terms of t divided by d1 and t divided by d2 as well as t divided by d1 d2 can be neglected. That means t by d1 comma t by d2 comma t divided by d1 d2 will be approximately equal to 0. So this equation will take the form, p1 plus p2 minus t p1 p2 divided by mu plus this whole term will goes to 0 if we are multiplying this. T by d1 is 0 plus 1 by d1 minus this term also will goes to 0, t by d2 term, and this 1 into 1 by d2 terms will exist. That means 1 by d2, and this whole term will goes to 0, will be equal to 0. Now we can write it as p1 plus p2, or I am just rearranging this equation, minus t p1 p2 divided by mu will be equal to 1 by d2 minus 1 by d1. Again we are considering our actual pictorial representation, that is we are considering our diagram. That means here you can see that this d1 is nothing but the distance of the object from the lens, as well as d2 is the distance of the image from this lens. So I can simply write it as d2 is equal to the image distance v, and d1 is the object distance u. So here 1 by d2 minus 1 by d1 will take the form 1 by d2 minus 1 by d1 will implies it's nothing but 1 by v minus 1 by u. So this quantity 1 by v minus 1 by u is nothing but 1 by f. This is 1 by v minus 1 by u is 1 by f. This equation is nothing but the lens maker's formula. So from the value of lens maker's formula, we can write it as 1 by v minus 1 by u is equal to 1 by f, and again we will get from this derivation that we can observe from this derivation that 1 by f will be equal to p1 plus p2 minus t p1 p2 divided by mu. Here you will be doubtful that here we are not applying this the sign conversion theory. That means we are derived this Gauss coefficients and this condition for image plane by considering the new Cartesian sign conversion and taking this d1 and d2 have with the d1 and d2 with the actual sign conversions. So here we don't have to apply again the sign conversion, which will make the whole conversion incorrect. So d1 and d2 have d1 and d2, we have to choose the values of d1 and d2 simply u and v. So we will get 1 by f is equal to p1 plus p2 minus t p1 p2 divided by mu. Here at the final stage I am just replacing the values of p1 and p2. That means p1 is we are already discussed earlier, p1 is mu minus 1 divided by r1 and p2 is mu minus 1, p2 is minus of mu minus 1 divided by r2 minus t into mu minus 1, or here mu minus 1 into minus of mu minus 1. So this whole term will negative, so this negative will become positive, mu minus 1 whole square divided by mu into r1 r2. I am simply taking this mu minus 1 outside and I can write it as into 1 by r1 minus 1 by r2 plus t into mu minus 1 divided by r1 r2 into mu, or I can write it as 1 by f will be equal to mu minus 1 into 1 by r1 minus 1 by r2 plus mu minus 1 divided by r1 r2 into t by mu. This is the final value of 1 by f, or the lens maker's formula corresponding to a thick lens. A thick lens. Now I can discuss very much easily by for the case of a thin lens. So I have the system matrix corresponding to a thick lens is 1 minus p2t divided by mu minus of p1 minus p2 plus t p1 p2 divided by mu t by mu and 1 minus t p1 divided by mu. Here the quantity t is nothing but the thickness of the lens. So for the case of a thin lens I can just consider that this t is very much low, or t goes to 0, or approximately I can take it as t approximately equal to 0. So this system matrix will take the form, this t will be goes to 0, 1 and minus p1 minus p2, this term will goes to 0 and this term will be equal to 1 itself. So it is the system matrix corresponding to a thin lens. So from this again I am comparing this system matrix of thin lens with the actual notation or actual system matrix values, or system matrix of an optical system B minus A minus D and C. So I can write it as the values of Gauss coefficient as B will be equal to 1 and I can take the chronological order. A is equal to P1 plus P2 and B is equal to 1, again C is equal to 0 and D is equal to minus 1. D is equal to 0 and C is equal to 1. A is equal to P1 plus P2, B is equal to 1, C is equal to 1 itself, and D is equal to 0. So Again, we are substituting these values of A, B and C in the lens maker's formula or condition for image plane to get the lens maker's formula, that is A d1 d2 plus B d2 plus minus C d1 minus d is equal to 0. It is the condition for image plane, and I am substituting these values in here. I will get p1 plus p2 into d1 d2 plus b having value 1 d2 minus c having value 1 d1 minus 0 is equal to 0. Again, I am dividing this whole equation by d1 and d2. I will get p1 plus p2, d1 and d2 get cancelled, plus 1 by d1 minus 1 by d2 is equal to 0. And also p1 plus p2 will be equal to 1 by d2 minus 1 by d1. Again, we have d1 is nothing but the object distance from our actual figure or our figure. This d1 is the object distance, so d1 is equal to u itself, d2 is equal to v itself. So we can write it as 1 by d2 minus 1 by d1 as, or this equation as, p1 plus p2 will be equal to 1 by v minus 1 by u. This is equal to 1 by f. Or we can write it as 1 by f will be equal to p1 plus p2, which is equal to mu minus 1 divided by r1 minus mu minus 1 divided by r2, because p2 is minus of mu minus 1 divided by r2. So I am taking this mu minus 1 as outside into 1 by r1 minus 1 by r2 is equal to 1 by f. It is nothing but 1 by v minus 1 by u. So this is the lens maker's formula corresponding to a thin lens. So it is the thin lens maker's formula and thick lens maker's formula. By this section, we are concluding the matrix method. You have to try the solved example in the textbook Brijulal and Subramahnyam, and also other problems you have to obtain. Thank you for watching.